Buongiorno, buon pomeriggio, good morning, good afternoon, good evening to those that are joining us from who knows where in the world. Welcome to Crossroads, data-driven talks on ancient materiality at the interface between archaeology, science, and engineering. So I'm really honored and incredibly happy to see such an incredible response of colleagues from the field to join this international workshop in the framework of summer field work organized by Course 1 Civil and Environmental Engineering at MIT, and it's really an incredible privilege to be here in Italy with my students that are interested in topics that we will cover today. As I said, it's a really incredible privilege to be here, also at the Museo Egizio, Egyptian Museum, and I'm glad to see Director Christian Greco here with us to introduce the workshop and also to really introduce this fascinating interface between different fields that more and more is allowing us to push forward the knowledge, and this crosstalk is really fundamental in order to be able to make progress. So, as I said, Egyptian Museum is at the forefront of this work, and Christian, give us your perspective of how data will enable us to actually move forward and allow us to explore new frontiers of knowledge.
Well, thank you, and good morning, good afternoon, good evening to everybody. It's for me an honor to have you here today, and I'm really delighted to see also some of your students here in presence and to see you back after these 2 terrible years we have behind our back. Why are we so interested in the work you're doing? Why do we want to become a crossroad? Why don't we want the Museo Egizio? I just correct you, we never translate it because I think we shouldn't translate it. Museo Egizio is a unique concept, and I think that it must become iconic, and we must understand what we mean when we say Museo Egizio, being one of the oldest institutions housing Egyptian collection worldwide, being one of the most interesting places where we have the material culture that can tell us something about the past. Why are we interested in true multidisciplinarity in this place? Well, first of all, because we are a museum. A museum is multidisciplinary by definition. When you do an exhibition, you have a curator, you have the collection manager, you have the static engineer, you have the communicator, you have the architect, and all together you build something. For us, having different scholars sitting around the table is not an option. It's the only way we have to move forward. Probably because we're driven to the fact that we have a material culture. And in order to preserve this material culture, we have to approach from different points of view. But what is a point of view of an Egyptologist and archaeologist? Well, I have recently written a book which I've called The Memory of the Future. And the memory of the future for me is the museum. Already in the 70s of last century has been defined a museum as a place of memory, i.e. a place of conservation. I do believe, though, that we are not only a place of conservation, we have a place of construction of memory. Of course, we construct memory every day, and society gives us the role to construct its own memory. Why do I say construct? Because it's almost impossible to achieve the truth about the past. There is extensive literature from the end of the 19th century throughout the 20th century, whether the past does exist or not, or whether the past only exists to be used by the present. And this is something that we have to keep in mind. Maybe what we approach in a museum is not true Egypt. When you go through the gallery, you will not see a true image of what Egypt was 2,000, 3,000, 4,000, 5,000 years ago. Probably we never reach that kind of knowledge, but little by little, we can come nearer. Being aware that every reconstruction we do is only limited, and it will be surpassed, and future generation will look back at what we have done and maybe criticize it or just keep the good points and go a little bit forward. From an Egyptologist, the material culture is a bridge in order to reconstruct human lives. What we are interested on is why people 3,000 years ago or even earlier thought about creating an object. Why? What did they put in motion? Why did they ask an artist instead of another one? Why did they go to a workshop? By the way, we don't even know. We constantly use the word workshop. We don't even know whether there were workshops in ancient Egypt. John Taylor, a colleague of ours at the British Museum, just contested the word workshop altogether. We don't know whether we had different groups of people working on specific material. Of those working wood were also working in stones. We don't even know whether we were constantly working together or working together when necessity arises. So we give for granted a lot of information which we don't really know. That's why it's so important for us to understand the biography of the object. That's why it's for us so important to instruct all information we might have from the materiality that put together with the sources and with our interpretation can help us to reconstruct the way that the ancient Egyptians were thinking. There are a lot of new development in our fields concerning how you can reconstruct different kind of things, even ancient noise, ancient perfume and scents, ancient way of perception, but all of this is in order to deeply understand their thought. What were the ancient Egyptians thinking and how can we reconstruct their life? Well, it's a huge task. It's speculative, as you might see, but we want to limit as much the hypotheses and speculations, of course, and base our data for what we can extract from the object that we house here. I want to wish you a very prolific day of work with one last thought, which really keeps me going all the time in the museum, which is the life of our objects. When I see the lifespan of our objects, I always have to think of what a colleague of ours, Malafuri, is a Greek archaeologist, say about the importance of the objects. Mankind thinks that he is creating the objects. Actually, yes, we do create the objects. We feel, we think we have a lot of power, but the objects are something peculiar. They live much longer than we do. And the Egyptians were aware of that all the time. That's why objects belonging to previous generation were sometimes brought into a tomb to see the continuity, for instance, in the royal continuity of power. But not only that, objects even create ourselves. It might seem strange what I'm saying now, but going from structural deformation and changing, even in our anatomy, anatomists keep saying that probably in 100, 200 years from now, we will see already some deformation on our thumb because we use our mobile phones all the time. But think on something else. Our society would stop immediately if we don't have very powerful computers that allows us to have energy, to have electricity, to assure that we have lighting and all our infrastructure work. So actually we are dependent in machines that we are created in order to work ourselves. And if we think of ancient Egypt, even mathematics which probably, together with philosophy, is the most abstract discipline that mankind has developed, would have not been possible without developing writing, papyrus, and ostraca. So in this interconnection, in what Ian Hodder defined entangledness, is where we find the space to operate. What is the interconnection between objects and subjects, and how, through the objects, we can build a bridge to past generation, but also to future generation. I also like to put the idea that the museum not only preserve the past, but also builds on for the future. And the objects that we are here really connect us with the past and the future. And everything you might achieve in order to better understand what we have in front of us is a little tiny piece of a puzzle that enable us maybe to come a little bit nearer to the past. It's also very reassuring that the objective past is not reconstructable, because otherwise we would be out of work, actually. But that's why we have to keep reinvestigating, because that is science, that is research, and so it's also very reassuring to know that what we write today, in 100 years' time from now, will seem completely surpassed, but that's the beauty of doing research, understanding that we, all of us, just contribute for a little tiny piece, and in a continuum of scholars and researchers that find in the material culture the primary source of inspiration. So I wish you a lot of inspiration today, and I'm really looking forward to hear the results of the interchange, and I do hope that more and more of you will be getting interested in analyzing and studying our material culture. So have a good and prolific day.
Thank you, Christian, and this cannot be a better introduction to our workshop, and you know, learning the past with the eyes towards the future, and how this knowledge that we accumulated over so many years might really be foundation for a sustainable future development. So thank you so much. I want to thank you sincerely, Museo Egizio, Christian Greco, but also Enrico Ferrari, exactly, who co-organized this workshop with me, and it's a great pleasure to introduce Professor Steve Weiner from Weizmann Institute to kickstart the work. There is a slight change in the program. Evelina Cristolin will join us after lunch for at the beginning of the afternoon session to say hi. And Steve, please, are you ready with all the slides and everything? Everything is perfect. So thank you, Christian, and it's a great pleasure to introduce Professor Steve Weiner, who somehow has been a guide also in my personal journey. I met him many years ago at a synchrotron facility in Berlin, in Bessie, and that first meeting was an incredible catalyst and definitely allowed me to design my scientific interests and directions. And Steve comes as a structural biologist into the field of microarchaeology, and he, I think, will introduce this concept. He wrote a fantastic book. I definitely advise my students to have a look into his book on microarchaeology. And without further ado, please join me. And we are looking forward to learning more about your extremely interdisciplinary approach to science.
What's the rule of the game here? Can I stand? I don't know where the cameras are.
Yeah, I don't know. Let's see. You want to, does he need to, deve sedersi o può anche?
Se vuole stare in piedi.
Puoi stare in piedi. Il microfono funziona lo stesso?
Sì, lo può prendere in mano.
Lo prende, ok? Ma senza microfono, cioè, perfetto.
Oh, I can stand then.
Yeah.
Okay. Great. And I move my own slides, yeah. So really it's a pleasure, literally, first of all, we're now all coming back to life and talking at least to a partial live audience. I'm sick and tired of this remote lectures when you're staring at your screen, so this in itself is an inspiration. But the subject matter of this day workshop is very much close to my heart. And what I wanted to say before I get into details, and it's all about details, is this slide. And I put it up here basically, but Christian just said in a lot more detail, perhaps the most important message that I can make, and the one that I've concluded from my own experience of more than 30 years working in archaeology, is that this is a difficult science. The biggest mistake that we can make when we're doing this work is to underestimate the difficulty. It's very easy to compromise and come to conclusions based on imagination and extrapolation and hypothesis. But putting a piece of the puzzle into place with a great degree of certainty is a real challenge. And I work most of my life in natural sciences, and there's standards which are acceptable, and I don't think the archaeological world should lower those standards to make a good story. The story should revolve around the facts. And what I want to present today is my effort to provide tools and to show you how these tools, which are new tools for the most part in the last 10 or 15 years, can elucidate a problem. In this case, it's archaeology, and we're going to go to an excavation. But the same... Yes. I haven't said anything. It's the same echo. So in this, but I think I work in excavations in the field, but I think a museum, in a sense, is an analogy to an excavation. You have the materials. They're not in situ, but embedded in those materials is a lot of information which, if you're smart enough, you can extract, and as Christian said, reconstruct the minds and the behaviors of the people that made these objects. So bear that in mind when I'm talking. So Admir mentioned microarchaeology. It's a term that I coined in a sense, or I adapted. Other people used it, but in my mind, it's like microbiology. It's biology that you don't see. You need some instrumentation to reveal. But it's all about archaeology. It's not about material science for me. It's not about analytical work, and it's trying to extract more information from the archaeological record than you can see by eye. And what comes out of the excavation sets the agenda. In other words, we don't work backwards and say, okay, I'm an expert in stable isotopes. Therefore, I am going to look in the archaeological world for a problem in stable isotopes. I go to the excavation, and sometimes for season after season, I don't know why I'm there, because I haven't identified a problem yet. But I'm characterizing it and looking for something which, in my understanding of the archaeology of the site, I think was worthwhile solving. And then the next step is, do we have the tools to solve this, or do we have to develop the tools to solve this? And most times it involves development of the analytical tools and then applying them. Okay? This is quite different from the way many archaeological scientists go around doing their work. I'm not trying to put down other people's approaches to work, and I like the Paul Simon song about there are 50 ways to leave your lover. There are 50 ways to do science. No one is more correct than the other, but this is my approach. So the end product, hopefully, is a better understanding of the archaeological site. Now, you can't do this if you don't understand science, and you can't do this if you don't understand archaeology. It's not a question of, I work until this point, and then I hand over the problem to somebody else. That does not work. And if you don't believe me, think about it. I've been doing this for 30-something years, and there are archaeologists who come very far along the path to understanding natural sciences, and I try to go as far along the path to understanding archaeology. I'm not an archaeologist, and it's with those people I can work, and we always work in a team. But if the archaeologist says to me, that's your job, or that's the subject I'm interested in, you solve it, forget it. I go, there are many sites. There are other sites. I go to another site. So you really have to understand natural sciences and archaeology. And then there's another dynamic which I learned firsthand, and that is when you're excavating a site, and this is the advantage in the museum, it's excavated, it's here, and it's not going anywhere. But when you're excavating a site, they are destroying the site. There is no way that you can excavate a site and record everything in a book or in digital form so that somebody else can recreate it. Because like in all science, you only focus on on the question, and you're blind to everything that's going on. You're not objective when you take a site apart. You take it apart in the way that you think will help you to reconstruct it. And so if somebody like me who wants to contribute to the understanding is not on site and does not have some sort of analytical capability on site in real time, I can't tell the archaeologist, stop, I need 24 hours before you excavate this, continue excavating. That doesn't work. I have to be able to have some information in 5 minutes or in 10 minutes. Take a coffee break, and I'm going to run and do some analyses. That's realistic. And then I can say, oh, this is boring. It's not worth continuing. Let's continue down, excavate. Or you can say, well, this is unusual. I'm surprised what's going on here. We need to look at this carefully. And if it looks more and more interesting, then we change the way that this particular corner of the site is going to be excavated. So you adapt the excavation strategy to the question on hand, and you work on an interactive manner all the time, running back to the lab, which is usually on site, by the way. I mean, the lab has to be there. And you come back with answers. You say, okay, now, based on what I've just learned, let's go this direction, this direction. And the end product is to go to your home lab with the best set of samples that you can possibly take, including controls. It is the very rare excavator who understands, both for the excavation and for the analytical process, it's all in the controls. Easy to take the sample that looks interesting, but what are you going to compare it to? And that's the biggest challenge, which is actually people. How many times somebody said to me, I don't understand, you came to work in archaeology and you're out in the field. Why? What are you doing there? I'm collecting the controls. I'm trying to figure out the input of the materials into the site and how the materials have changed, but I have to know the natural materials. So on-site excavation, and here you can see an example of our on-site lab. Right, on-site, literally. And the key component is an infrared spectrometer. This is a very old version. I'm going to talk a lot about infrared spectrometry. We usually have a petrographic microscope on site. Sometimes, but it's not very useful, in my opinion, is an elemental XRF, what you were doing yesterday. Doesn't really add much in reality, for me at least. So what's the workflow then? You can guess. Everything starts in the field. And this is an example of how Professor Elisabetta Buaretto, who is now the director of the Kimmel Center, how she works. She is in the field a lot. And there on the top left-hand side is Elisabetta sampling. And her interest is chronology. And for chronology, it is absolutely crucial to be sure that this material that you're going to date, nobody's interested in the date of an olive pit. They're interested in the date of the context in which that olive pit was found and how it relates to the material culture of the site. And so you have to make absolutely sure that that context is telling you about the question that you're interested in. And that requires understanding the context. For example, only charred materials, for all intents and purposes, are preserved. Maybe not in Egypt, but in the rest of the world. And if the charred olive pit is not in a context in which it could have been charred, then clearly it's been transported from some other place where it was charred. And you can't leave that open for saying, oh, okay, we'll run the sample, and if it gives a date that I want, then it's a good date. That is what you would say in polite English, BS. That is not science. So you have to collect a sample, be sure of the context, and say, I have to live with that date. And that's doing science. So this is the key step in the workflow, especially for radiocarbon dating. And then there's sample preparation. And of course, there's a lot involved there, cleaning it up and so on. And Elisabetta is one of the few people in the world that has her own research accelerator at the Weizmann Institute. And in this way, she too can tune the instrument to the question at hand. If she's going to date, for example, a site which we just finished a long project on, in the southern part of Israel, the first known location where Homo sapiens arrived in the last wave out of Africa, turns out to be that the date is 50,000 years. 50,000 is the very end of the effective dating period of carbon-14. So to do that, before you run one sample, that machine has to have a very low background, so that you don't end up saying it is older than my background, but giving an absolute date. And that's what Elisabetta managed to do at this particular site of Boker Tachtit. Or in historic archaeology, it's not a question of living with the limits of the calibration curve or whatever. You can work around the calibration curve if you can analyze the stratigraphy, the layering, and then date down to a resolution of, say, a year, if you are good enough and you find the right location to do that. So at every extreme, there's a huge challenge, and this field of chronological research is really taking off because a historical subject without a chronological context is lost. So I'm going to continue this lecture by taking you to one archaeological site, which happens to be 20 minutes drive from my house. And as I live on the campus, it's 20 minutes drive from my lab as well. And that's Israel. It's a very small country, but it's so dense with archaeological sites. So we're going to Tel Katra, and I live about here. And this is a site which was a salvage excavation, which means that they're going to build apartment buildings on this site. And by the law of Israel, you have to excavate the site if there are archaeological remains and preserve them. And in this case, sometimes part of this area will be preserved between the buildings so that it can be preserved for posterity. And it's a Byzantine site, and it was apparently a spa, a sort of a place like a hotel or something, and an industrial site. It's a strange concept for us to put it together, but that's what they did. This is what, on the left-hand side, this is the type of typical look about this archaeological site. And a lot of mosaics, very well constructed. And there's even a games room, and showing that this wasn't a spa. The owners of the spa provided entertainment for the crowds. And you can see different games. Does anybody recognize that game? Come on, some of you know it. Yeah. What's it? Yeah, exactly. It's called Mancala. My granddaughter taught it to me before I went to the site. And I played, and she beat me all the time. This is, you can buy this game in any store for children's, in Israel at least. And if you read Wikipedia and believe Wikipedia, it goes back thousands of years. And there it is, Mancala, 1,500 years ago. So I published 2 papers on the subject, and I want to tell Admir that to pay attention to the fact that I'm the first author, which means you've done full circle in your career. You were no author, then you were first author when you were the student and you did the work, or the postdoc, and then you're never the first author because everybody else is doing the work, and then, if you're lucky like me, you can retire and start becoming first author again. That's my aim in life. So in this site, it was huge, and we kept visiting the site to follow what was going on, and we planned to spend 3 weeks at the site with the lab on the site and to focus in on issues and questions. And because we'd followed it, I kept my eye on a huge section which they had excavated. It is, you can see this is a 2-meter pull, so this thing is about 30 meters. And it's actually amazingly overlaying a mosaic floor. And to my eye, I didn't see what was going on in the beginning, but I was attracted by the fact that they'd exposed this fantastic section. And I was going to try to see if I could identify an interesting problem in this section. The first job is to clean it and expose it. And when if you came to our field school, which we have every year, you clean the section yourself, because you learn more about the section during the cleaning than almost at any time afterwards, just to get a feel for what you're up against. So let me read the section for you. First of all, you can see there's a silo. That's clearly intrusive and late and has penetrated through all the layers. But there are other features. Does anybody recognize some intrusive features?
US dollar.
The what?
USD.
USD. You got your priorities wrong. Never occurred to me. It's not worth much. There's a pit that was dug into the section here. There's another pit that was dug into the section here. And a feature which absolutely boggled my mind was the fact that the sediment that's exposed in this section only here and over here, but you can trace it, it covered the whole section. That sediment contains shards and contains slag. So that's not a natural sediment. These guys went somewhere and brought sediment to the site in order to cover whatever is here. So this is an artificial material, artificial in the sense that it's been translocated to the site, which I thought usually they just dug into the site or whatever, but no, that's not the case. So we're going to focus on this area in the middle, which is not intrusive and original. And it doesn't look like much. I'm just taking a look at it. And before I started, the archaeologist who'd been excavating there she just said it's another dump of pottery, because there's clearly kilns for pottery, pottery breaks, pottery when they're firing it produces ash, and so almost every other section looked like this. And you can see that this section doesn't look very different from that section. There's ash here, just huge amounts of broken pottery, and so on. And we can see that over here. And here, down here, is a lot more ash. So I started taking a great interest in this lower deposit, and especially that gray material in this material. And so the first thing we do is run an infrared spectrum. Now I want to walk slowly through the infrared spectrum and the interpretation here. The red is the gray sediment from here. And you have 3 components which we can identify. And these are the standards from the standards library that we have. So calcite, it has a peak, a major peak here of the carbonate, but this peak is not exactly superimposable on that peak. Already a hint that something's going on here. This is not normal calcite. We have the 873 peak over here, looks the same. We have the 714 peak of calcite, great in this, very well developed in the standard, but very poor in the powder, in the gray powder. Another hint, something's going on. We have opal. Opal is characterized by this peak not being split. Here it's slightly split, but it's almost symmetric. And there's an absence of a peak here, which is present in quartz, which is not in this side. But there is another mineral phase, cristobalite. Cristobalite is a high temperature phase of SiO2. How do I know it's cristobalite and not quartz? Because of that peak. 621 is present in cristobalite, but not in quartz. So everything is pointing to a very unusual situation. And so now let's go one component at a time and ask, what is the material that is contributing to this type of mineral component? Cristobalite forms at temperatures above 700 degrees centigrade. So if you isolate the opal component, or even just take a look in a light microscope, it is full of phytoliths. These are the silica bodies that are produced by plants. And in this case, it has amazingly large multicellular silica. There are cells that have produced so much silica that it's fused together. And if you look, you can see that there's charred organic material inside these multicells. And this material contains a lot of birefringence. Birefringence tells you the material is crystalline. But I told you that there's opal there. Opal is not crystalline. It's anisotropic, so it should be black when it's birefringent. So the birefringent component most likely is the cristobalite, because it's a crystalline component. And if you look at in more detail in the scanning electron microscope, you see that these phytoliths are curled and melted and so on. Everything points to high temperature. And phytoliths melt at about a temperature of 900 degrees. Our colleague Rosa Maria Albert from Barcelona analyzed the morphologies of these phytoliths, and again, to our surprise, the whole assemblage of phytoliths there all come from the stalks or the chaff of wheat. Now, that was not expected. If you're going to make pottery, because this is an industrial site and there's pottery shards everywhere, why on earth is there so much stuff that you would feed to the cows or something? And I was perplexed and took a look in the literature, and there are well-documented examples, and this is from Egypt, of using chaff to fire pottery. If you have the right kiln and the right oven conditions, even though the stuff burns very quickly, it gets to very high temperatures, and there you, at least these guys know how to do it. I wouldn't know, but is an example at least, which reinforces the concept that this is not necessarily a contradiction. So if you look carefully in this section, you can see blobs of green material, fused stuff. And if you look at this, take a piece of that, make a polished section, look in the scanning electron microscope, at the backscattered image detector, you'll see it's a glassy phase with a lot of pores. Clearly, this has been this is melted and solidified with cooling. And if you look just around this here, it's embedded in the gray material, and there are phytoliths attached and integrated into this slag. So this is a phytolith slag, actually. And I've come across this time and again. People say, because it's so conspicuous, this slag, any excavator would say, and it's green, people would say, well, here we have a metal workshop. And then we would analyze it, no metals. And it was only here that I could associate this type of a slag with melting of phytoliths. So what we've established up to now, the temperatures are certainly above 700 degrees of this gray powder. We've tested Gadara phytoliths, trying to home in on conditions, and in the oven, they melt at 800 degrees centigrade, or 900 degrees, depends on the conditions. And the slags are generally found below the ceiling of the structure. It's the hottest area. So we're making progress, but we haven't literally found what the smoking gun, and I excuse the pun. Can we really nail it that this was a kiln and not an accumulation of material from a kiln? So I want now to I'll come back to that issue, and I want now to talk about the calcite component in the gray sediment, this component. The calcite, when you burn chaff or hay, there's not much calcite, because in the origin of calcite in ash is actually the burning of calcium oxalate. Calcium oxalate is CaC2O4. And at about 400 or 450 degrees, there's a solid state reaction in which carbon monoxide leaves the structure. And if you just take out one carbon and one oxygen, you get calcium carbonate, which is calcite. So ash calcite is formed in a very different way than calcite from a solution or plaster calcite. So it has a signature, it could have a signature which is characteristic of ash calcite. So again, infrared comes into play, and I'm going to tell you now about one of the most powerful analytical techniques that we have for this type of archaeology. And that is to be able to differentiate between calcites that are formed in different ways. In a sense, it's converted to more ordered at the atomic level or less ordered at the atomic level. The problem is that to do an infrared spectrum, you have to grind the sample. I know you can take samples now off the surface, but they are not as reproducible as we need, and they're distorted, and it very much depends on the contact between the diamond and the surface. So I don't like that method. But since the 1950s, when this method of using a ground pellet embedded in potassium bromide, which doesn't absorb in the infrared, people realized there's an inherent problem, and that is that the more you grind the sample, the sharper the peaks become. And this absolutely negates the possibility of doing what you do in X-ray diffraction and measure the broadness of the peak to assess how disordered the atoms are at the atomic level. And so the message I got when I had learned how to do infrared spectrometry was grind the sample well and you'll get a reproducible spectrum. And that's what you did, but you could not extract this information until a former student, PhD student of ours, had the blinding insight to do the following simple experiment. And that was, he said, look, I can't control particle size in order to compare samples of the same particle size. But I do know that if I grind the sample again, the population of particle sizes is going to get smaller. That is a fact. So if you take this single crystal of calcite, geological calcite, and grind it lightly, you'll get a point over here in the space of just measuring the heights of one of the peaks versus the normalized height of one of those peaks to the normalized height of the second peak. They're all normalized to the main peak. Very simple. If you grind it again, you'll find that you've moved in this direction. Grind it again, you go down the grinding curve. But it's all the same sample. But now, if you take limestone and you do it, the grinding curve is shifted in this direction. And if you take wood ash, it's over here. And if you take plaster, it's over here. In other words, what's happening here is the curves are shifting according to the degree or the extent of disorder of the atoms, which in itself tells you about the way that calcite formed. So here we have one of the most common components in an archaeological site. We can differentiate its origin based on this type of characterization. So we also did a theoretical study with a colleague of ours at the Weizmann Institute who calculated the infrared spectrum and then distorted the atom positions, and he proved, based on first principles, that this is correct. The degree of disorder increases in this direction. So where does the calcite fall from the gray powder in the section? To right on that curve, which I haven't mentioned, Leo Regev, who did this work, for some reason, which until I got to Gadara, but it was 10 years after he produced this data, he decided it would be interesting to take wood ash and heat it in an oven again to 900 degrees centigrade and then measure it. And it was even more disordered over here. And lo and behold, the calcite from that section in the gray powder, all the samples fell in the distribution around that pattern. So here was proof of the fact that this calcite had been heated time and again and had become very, very disordered. We'd never encountered such a calcite in all my experience, at least in the field. So that's one game. Another game that's very, very helpful, and that is that clay is very sensitive to heat. That's why you produce ceramics. It undergoes all sorts of chemical reactions and so on, and as you heat up clay, you can see that the infrared spectra change their parameters. There are the hydroxyl absorptions around here, which disappear above 400 degrees centigrade. The main peak shifts from about 1030 to about 1080, something like that. The peaks over here change, become less and less prominent as you go up in temperature. So I used this tool to try to find what I called the smoking gun. And at this point, I knew I sort of was trying to hypothesize that this really is an intact kiln, but it didn't look that way very easily. But when I found at this location, that sediment that covered this thing, this is a bit of a mess, all the ash had distributed over the section, but on this side over here was the sediment that covered this structure, and this is the inside. Everything to the left is on the inside of the structure. And I ran the infrared spectrum from the cover, clay, and this is clay not heated. You can see not even to 400 degrees because these hydroxyl groups are here. But when you move 10 centimeters over, at the exact same location, 10 centimeters from the roof of the structure, the clay has been heated. And I could repeat this 5 or 6 times at different locations. So that was a hot contact. And that's the smoking gun. So in order to really say, okay, I am convinced that this is a kiln, we did all this work, which could not have been done if I would have taken samples. I would never have had those samples to analyze in this way if this work would have been done in the lab afterwards. So now I want to finish off with telling you something else which I think is probably the most significant part of this study. I noticed that in this bottom chamber, we had, you can see that here in the high magnification, we have layers of ceramics, broken ceramics that sort of formed a floor of the firing chamber. And so what? But I noticed that some of them were dark and brittle like a ceramic. You couldn't break them just without a hammer. But then there was in the same layer ceramics which were light colored and I could just friable. I could just break them with my hands. And I try to ask, okay, what's the difference between those things? What's going on here? And of course, we do what we know how to do, and that's run infrared spectra. And to my astonishment, if you look at the 514, these 2 top spectra are of shards from the top of this material. And they show the characteristics of shards, heating, none of those small peaks, 1078, that's high temperature, maybe 800 degrees. It's a very small peak over here, all what you expect from a shard. You go to these shards, 563, 564, you see the same thing. You go to the friable shards, 569 and 570, and lo and behold, it's a shard. It's not a sediment. The hydroxyl peaks are back. The main peak of the thing is around 1035 or something like that, and these peaks are back. And this is the spectrum from the local sediment. It's identical to that. So what's happened here is that the clay in those shards have recrystallized all the way back to becoming a crystalline clay again. And it was mind-boggling, not in the sense that nobody had ever reported such a phenomenon. It's been reported for glass, which is a key to perhaps what might be happening, that glass recrystallize or devitrifies. But clays, I'm not aware of any example like this. And so we did X-ray powder diffraction, but I think I should round this up. But I do want to point your attention to the fact that those recrystallized clays did contain other components that were a giveaway if you would have gone and looked for them. And one is the presence of zeolites. These are low temperature forming crystalline silicates. There's a lot more montmorillonite, the original clay, in these samples than there is over here. There's kaolinite, a very stable clay, which you don't find in the sediments, the natural sediments in this area. and so on. So there are other elements or other minerals that formed because of this crazy recrystallization back. And there are, I think, important implications. And this is that, first of all, we've demonstrated that recrystallization can occur. Because, you know, you heat it up, it's in an unstable environment after heating. There's nothing thermodynamically to prevent this recrystallization process. And in fact, now you can turn it around and say, what does prevent recrystallization in a ceramic? I don't know. But we do have independent evidence that what is unique about those shards is that they were heated time and again. The calcite story, and the fact that it is the floor of a firing chamber, which was presumably fired many times. And then you could say, okay, well, if that's the case, and I say if, then here we have maybe a new tool to identify shards or ceramics that were repeatedly fired. And what are those? Cooking pots is a good example. A taboon oven is a good example. Or other circumstances which could tell us repeated heating. And that would now be a new tool in the toolkit for archaeological science. So the conclusions that I want to, the more the take-home lessons for this long story, is that microarchaeology is all about integrating the macroscopic and the microscopic archaeological records in order to solve an archaeological problem. That's the main option. On-site capability is invaluable. We need to understand archaeology and the natural sciences to do this and to know and to try to push it forward. And elucidating basic mechanisms is the key to deciphering the microscopic record. Leaving it at the empirical observational level is only halfway, and you don't extract the ultimate potential. And so that's what we do. And we have a lot of fun doing it. Thank you.
Can you hear me? Thank you so much, Steve, for this setting the ground, and we really appreciate. We might have a few minutes for questions, students. Yeah, here. Wait.
You mentioned during fieldwork you need to focus on the question that you're asking when you collect specimens. How do you determine the question? Because you mentioned how this finding, a lot of people would have looked over the things because they might have thought that they were just metals and looked over it. How do you know that a certain sample is significant? Or do you take everything and test it and see what happens?
Yeah, that's the heart of the question, the heart of the activity. We spend a lot of time probing around, but so do I do that in my research in natural sciences on mineralized tissues. I don't know what's interesting or a priori. So we putt around here and putt around there, talk to people, come to conferences, chat and interact and so on. And that's the same thing. We can spend sometimes season after season. In this case, it was in a sense lucky, but lucky in serendipity is for a prepared mind in a sense. I knew that when we had a section like this, which is highly unusual, it's only because it was a salvage excavation, that within this intensive activity, maybe there's going to be a story. And that's how it works. You can sometimes waste a lot of time, and I can tell you those over lunch.
Yeah, but you know, you are with your instruments directly in the site. That's the privilege and approach that.
But we're not systematic. This is not a question of being systematic. It's a question of probing.
Fantastic. Anyone else wants to ask?
Yeah,
Professor Roberto Gobetto.
Thank you very much for your wonderful presentation. I am asking if a combination of other techniques can give you further information. Let's say, for example, expert of solid state NMR and calcite, solid state NMR and calcite. So the line broadening of calcite can have complementary information of what is the real, let's say, amorphous or less amorphous crystalline size. Also, for example, by doing relaxation time on the carbon-13, you can have the same information.
This echo is very difficult.
Sorry.
So the question,
The relaxation time of the carbon-13 can afford in some way the same information. I am asking if for having all this kind of information, for example, you are following, you present beautiful results on the infrared spectrum and so on. But I am asking if, in any case, you are using other techniques.
Oh, absolutely. Yeah, so the bigger spectrum of techniques.
The answer is, I showed you an example of how we work in the field. Now I can make my own echo. Yes, of course, and the trick is to go back to your home lab with the best set of samples so that you can nail the answer. And at the home lab, we do everything. If we need solid-state NMR, we'll do solid-state NMR. We do a lot of X-ray, everything we do. So yes, no, this is just this part that's that's at the excavation. But in this particular case, it really, there was no, the phytoliths, the XRF, because we had to prove it was a phytolith slag and it wasn't a metal slag. There was a lot of stuff went into that. Yeah, but you throw everything at a problem. Archaeology is tough. You can't just relax and be a good old biologist. Far too difficult.
Great. I think we will move forward with the next presentation. And thank you again, Steve, for a wonderful opening talk. So it's a great pleasure, absolutely, to introduce Costanza Miliani. And I know Costanza for many, many years, and I remember her traveling around Europe in this little van packed with the coolest instruments you could find on the earth, doing exactly what is the most challenging task, to collect information in the field, outside your comfort zone of your lab, without taking any samples whatsoever. So I think she will tell us about this today. So thank you so much for joining us.
So thank you very much. It's a very great pleasure to be here. The title of the seminar is so inspiring, also for me, that I'm doing this job since several years, so I can imagine how inspiring can be for you that are maybe starting this in the future. So I keep some of the words of the title because are good for the presentation, and one is Crossroads. And I'm going to speak about MoLab. MoLab is a mobile laboratory and is working for artwork, heritage object, mainly in museum, but not only. And the idea started here in Italy several years ago. I was doing my PhD, so it was around 98. And I typically say that this was coming from the genius loci of the country. We have a lot of technology. Of course, we have cultural heritage. Our cultural heritage are spread and are diffused in the territory. We don't have one big museum as in France, the Louvre, where there is a very big laboratory there. So we have several museums with a lot of heritage. And so for this reason, it's important to have a mobile laboratory. So a mobile laboratory that can serve the different heritage and needs that are on the territory. Also knowing that moving an object is not easy for several reasons, for reason of risk, for reason of cost also. There is a high cost for moving an object from a laboratory, from a museum to a lab. And also from a very peculiar analytical point of view, I am an analytical chemist. If you do a sample and you do a lot of very fancy measurement on this small sample, the heterogeneity of all the object, of the stratigraphy, of the different points is so high that this small sample can be informative, but not of the whole. So with non-invasive method, we may lose some information, but at the end, all the picture is very clear, or many times is very clear. So we, in the years, built a very advanced laboratory that we move around in Europe, as Admir said, and we move with this box, something like a rock and roll band. We arrived there, and for 3 hours or 5 hours, the museum people are crazy because we came out with all type of laser and all sort of things. But after half a day, all is set up, and there is a very super lab working with the people at the museum. This is another very important point. No. Okay, so this started, as you said, in Italy, in Perugia. That is a small place where I did my PhD. I did my PhD developing a new equipment, portable equipment based on fluorescence spectroscopy. Then all started, and was the right idea in the right moment, because now, at 2020, we are coordinating a European laboratory made of the best mobile and non-invasive equipment in Europe. Why European? Because this needs the advancement. So I prefer to have the best optical coherent tomography in Europe, that is from Aida Liang, that is going to speak this afternoon, rather than having one in my own institution. So I really going to pick up the best competencies around. And since it's a mobile, so the people are traveling from Fort, that is in Greece, from UK, from Italy. We join together in a museum and we work together there. These that you see here are more oriented to museum object or mural painting, church, something like this. Now we are moving toward archaeological sites, so we have introduced remote sensing, geophysics, and the idea to have a laboratory, as you said, is very nice. It's not non-invasive, but it's another type of application, but I like very much. So some case of this type of work, they are some of them in Italy, some of them around. The first is for Herculaneum papyri. I know you are going to be in Naples or nearby very soon. So this is a sort of wonderful type of object. It's a wonderful case. Are those papyri that were in the library of the Villa dei Papyri that may you know or maybe have seen as a copy in Los Angeles. And Villa dei Papyri was one of the best biblioteca at that time. There were the early philosophers writing the early Greek philosophy. And due to the Vesuvium eruption, we have these papyri arrived to us as they were. And this is the only possibility in the world, because in other case, all the Greek philosophy we are studying is copy of copy of copy. We do not have the original. This is the only original written part by Epicurus and others that I don't know. So you even see the triangle of the first type of geometry. So it's something completely outstanding. So they are survived thanks to the eruption, but unfortunately are in this state that you can see here, they are completely carbonized. So from a scientific point of view, very challenging, because it's true, it's very difficult science what we are doing, and it's completely challenging trying to unroll these, trying to read carbon-based ink versus a carbonized papyri. Okay, so from an analytical chemistry, something that you say, no, thank you. But there are a number of researchers that directly approach these rolled papyri with X-ray method, phase contrast X-ray method, that although we are speaking only about carbon-based things, can see some differences in the structure, and was published on Nature, and others. So this is not our paper. Just to show you here how nice is this virtual unrolling. So it is possible to see through the roll, to see the different layer of papyri. In some cases, as here, some words. So from a scientific point of view or from an experimental point of view, is super, super cool, published on Nature. But as an added value for the philologists, so from who want to read, is yes and no, because there are some words that you can see, beta, alpha, and not more. This was done at the synchrotron facility in Grenoble. On the other hand, most of these papyri, at the end of the 19, were mechanically unrolled. So there is this machine, very nice machine, you can see at the library, was invented by a restorer that was working there, 1816, 1819, and it's called a Piaggio machine. It's not Piaggio as Vespa, but it's still very cool. And so he bravely, because now no one would have done this, with this mechanical stretching was opening this papyri, okay? And most of them were opened, with the results that can be seen as a disastrous. But now there are a room full of these, with all these fragments that still are unreadable because are black on black. So we decided to apply for an ERC project that is the most important type of funding in Europe, is for fundamental research. Me, together with a philologist, so I was doing the scientific part and he's the reading, the value of the materiality that I was trying to discover. We got this ERC. The project is Greek School, and we are going together. So we are trying to make this word visible, and he's reading and editing and writing for the first time the true Greek philosophy. And so these are the fragment of the opened papyri. And really, if you see there and you don't know nothing, you would have thrown away, because it's nothing there of an heritage. But starting using visible light in the near infrared light, the word came out from the black of the carbon. And if we apply something more special than a simple photography in the near, so using hyperspectral near spectroscopy, where we can select precisely the type of wavelength that gave more contrast, then we can apply statistic and some algorithm, we have 20% more word readable than before. So this is not a fancy virtual unrolling, but really we are giving knowledge to the papyrologist. And this was already a success. Then we tried to apply other methods. This is something that you try to have some information. It's so challenging that sometimes we decided to go there with an equipment to see if something came out. We tried with X-ray fluorescence mapping with Paolo Romano, that is a great scientist from Catania. And we decided to try, because actually it was carbon over carbon. But something came out. I cannot show all the map because under embargo we are sending the paper right now. So this line that you can see here in the imaging, X-ray fluorescence imaging, sorry, so we are mapping the different elements, and then we have an image for calcium, an image for lead, and so on and so forth. So we have discovered that these papers were organized, these papyri were organized with column and row. And this was something never known. And the line and the column were made with lead. And so this is another understanding to have a full knowledge on the immaterial value of this object. And then now we are trying to do something related to the roughness, because they are terribly rough. And this is a 3D model acquired with photogrammetry, because what is the point of the philologists? During this unrolling, on several pieces, you have a lacuna or an isola, an island, that is actually, there are some words, but are actually coming from another folio. So they are doing a sort of incredible, difficult puzzle. So we are trying to inform there if the words that are there are for sure of this folio or rather for another one. So we are now moving to study the depth, not only the surface. Okay. So speaking about X-ray fluorescence mapping, this is a very important method in our field now, because as others is merging the information on the chemical material, so the elemental composition, together with an image. And we have learned that this combination is very powerful, because many of these objects have the significance through the image. So if we can combine chemical information with the image, we are very informative. And X-ray fluorescence mapping is one of these. And these, I would like to show these two images because Paolo and the colleagues were here. And this is which was the question, to try to reconstruct the lost polychromy. So this is a wonderful papyri. I don't remember the period. Maybe Enrico can help us, but.
Yes, from the Polychromy, the provenance is unknown, but actually we suspect that it's from the Theban area, so Luxor, West Bank. And
maybe they can see?
Not in the moment, because it was in an exhibition connected with all our study together, and now is about to come back, but unfortunately is still not in the room. Yeah.
Okay. Yeah. So you see this fragment again of a papyrus, and those parts in color are false color, where the X-ray machine are seeing one element or another, so copper or iron. So the powerful of the method is that we gave an image, and so we can reconstruct the polychromy how it was. There is a sort of intuition or speculation, because copper, we don't know if it's copper carbonate, copper sulfate, but most probably is Egyptian blue, and I'm sure that Giacomo Chiari will tell you all about, so I'm not speaking about. And iron could be an ochre. Typically, we add to this elemental information some molecular with infrared spectroscopy that we use in reflection mode. that is even more complicated for distortion, but still very informative, or Raman spectroscopy, or X-ray diffraction, also in non-invasive portable way. Okay. This was short. This is long, is the third case. And I'm going to give you a long story short. It's a project we did on pre-Columbian, I learned we cannot say, Mesoamerican codex. And it's a long project, so I can tell you, I will like to tell you only the final story with some in-depth on some analysis. So pre-Columbian codex, or 16 of what for sure was an enormous corpus of manuscript. And why? Because they were treated by the Spanish conquistador, and they were seen as something made by the devil. So they were completely destroyed, everything. These 16 that are survived are, by chance, or for a reason, in Europe. Why? Because they were sent to the king that were paying the mission to America as a gift, a naive gift, okay? And so for this reason, they are now in a museum or library in Europe, after some difficult story, because at the beginning were not recognized or has something important. And in this mural painting by Diego Rivera, you see the fire and all these books that were destroyed. So this, in the slide, are the different codex that are surviving, that are mainly in Europe. They are coming from slightly different parts, and they are coming from slightly different civilization, but not so much. So we worked to this project together with an expert of Mesoamerican culture and expert of this codex. We really started together from the beginning. And these codex were never studied, being so precious, unique, so no one would have think to go there to take a sample to know if there is a blue or a white, which type, no one. And that's understandable. So when the MOLAB laboratory arrived, they asked us to study some of them, and then we completed almost all. And David Buti, that is at that time PhD student in my lab, was somehow the principal investigator of all this. He's the more in the field, together with the archaeologist and the archaeologist from University of Bologna is Davide Dominici. Okay, so first of all, I would like to show you some setup, experimental setup, because this mobile laboratory has to be very flexible. So we go in a museum, we have to study an object, but there are different objects with different problems in terms of conservation, also type of rule of the single museum. For example, these objects are more or less the same as a structure, but the different museum had different rule, and so we adapted the setup according to this rule. And so this is in Bologna. It was the first. This is at the British Museum, and this is, you see all the person around, because this is really coming a work done together with different disciplines. And this at the Museum, the American, you see they decided to have this rigid panel instead of the zigzag approach. Nevertheless, we adapted to what they ask to us, and we have a sort of mobile workshop also to change the different angles, and so we are able to adjust the setup being there. Okay, so these are all the codex, the different type, and where they are now conserved. Some results. Starting with the Maya blue. Maya blue is a very famous pigment. I don't know if you have already studied. No? So it's very interesting for us as a chemist in the field because it's a hybrid. It's the hybrid material. So you have a host that is a clay with several channels, and then you have a guest that is an organic dyes. So organic dyes are used a lot in art, in archaeology, but they are very sensitive to humidity, light condition. So this hybrid material is making the combination of the stability of the clay and the color of a dye. So it's something wonderful because they were able to see this opportunity, and now actually there are applications of this combined inorganic-organic material for several types of application in medicine, in color, and so on and so forth. They were studied by every scientist in the field, Giacomo Chiari, so everyone has to have a paper on Maya blue. And there are also different hypotheses on, because this molecule is the indigo, that is the organic dyes, that one. Okay. So there are actually several hypotheses on really where the indigo is in this structure. Nevertheless, we were more oriented not to study the structure, because this has to be done in laboratory with a sample, but to see which is the differences of different type of production on the different codex. So we applied what is possible for this pigment, that is combination of visible spectroscopy in reflection mode and infrared spectroscopy in reflection mode. And we also, that this is quite typical on our way to proceed, prepare in the lab several mock-ups or several reconstruction, because we need to have a lot of standard to be able to have meaningful information from the real object. So we treat this indigo with different clay at different temperature, a different amount of indigo versus the clay, and we learned how these small differences on the visible spectrum can inform on the different temperature and different type of procedures to produce the pigment. And then we bring this experience from the reconstruction to the real cases, because it's the same method that we apply on mock-up and we apply on the object. And so we are now able to do a sort of map on all these codex studied with a different method. Another point was also we found the use of sepiolite instead of palygorskite. And then studying all this blue, that we were confident all being Maya blue, but we were trying to see more differences with different production. It came out a completely different spectrum. And this was a big discovery, the use of comellina, that is a completely another type of organic compound, is that one. Again, was used with the clay, so we discovered step by step that this idea of apply a clay with a dye was not only for Maya blue, but actually was used for several types of dyes. And comellin was the first time ever that one discovered this dye used as a pigment. And this is really because we were doing non-invasive method, because if you do 100 points, you have more chance to come out with something anomalous. And this is the appearance of comellina. Is a little bit degraded because it's much more subjected to light degradation with respect to Maya blue. Then there are in this codex a lot of yellow, orange, reddish color, and we discovered they being all organic compound, all compound coming from plants. And that means that from an identification point of view, these are very challenging. We use fluorescence spectroscopy, UV-vis spectroscopy, but it's very difficult to arrive to the molecular composition. So with a non-invasive approach is quite good now. I would say that we are very good for inorganics because you have X-ray diffraction, Raman spectroscopy, FTIR. But then when you go to the field of organic compound, this is very difficult. So nevertheless, we have seen that there were some type of yellow, orange organic, and still the clay. So this idea to use a hybrid is for all the pigment. So we started with the reconstruction. We studied all the type of species and so on so far. And we tried to have a new method for recognize at least the macro chemical class. So carotenoid versus flavonoid, for example. This is possible, but not so robust. We applied Raman spectroscopy that in principle is good. You know Raman spectroscopy? So and so? You have studied? Okay, so yes, good. And so Raman spectroscopy is an infrared spectroscopy. Infrared meaning that we are studying the movement between atoms, so it gives molecular structure, but with another physical way. So it's a sort of alternative of infrared. And it's quite good also for organic dyes, but it's very difficult to be applied in situ. And also it became covered by fluorescence. So we were able to optimize the method for mock-up, but unfortunately was not working for the real objects that are much more complicated also for the aging. But the very end of the story, thanks to the help of this co-worker that was with us for all these years, is the fact that we have found only, always, only colorants that are coming from flowers, from the root, from the flower itself, but only coming from this type of origin. And these codecs were used to communicate to the society, the religion, the way of organized society. And during this communication, the codecs were singed, so there was a singing. And the singing was called speech of flower. So there is a strong link between the materiality and the meaning, between the materiality and the use of these codecs. And so this was possible again because we had a large amount of data. And seeing all these type of different organic dyes coming from flower, the expert of Mesoamerican culture came out with this interpretation that is very nice. Yeah. So as a structural point of view, let's say as an organization, this super European laboratory is working under a European umbrella that is called research infrastructure. And this is something that Europe is financing with the idea to have very big laboratory, but open. So everyone in Europe can apply, presenting a project. There is a selection, and who win have the laboratory for free in situ for 2 weeks, 3 weeks. So this is the way that all this traveling in Europe is supported. We have 3 platforms, actually, in this infrastructure that are following the needs, or what we are together thinking are the needs of the field. So there is a platform where the scientists can apply to go to see archive. In our field, there are unfortunately a lot of gray literature. So there are a lot of museums that has wonderful reports but are in the scaffold. They have wonderful image, they have sample. So with this art club, the scientists can go in the place and see the document, let's say. Then there is MOLAB, and you know all now. And then there is Fixed Lab, that is the access to very large laboratory. Synchrotron, neutron radiation, also PIXE, you know, under the Louvre, there is a super laboratory and is an accelerator of particles. So this is laboratories also inside the infrastructure. And then is the last 3 minutes or 5 minutes, because in the title of the seminar is data-driven, and this data-driven, I think, is really the future. I started my PhD thinking to non-invasive. Now, at the middle of the career, I'm sure that what we need for the future is data handling. And for this reason, we are trying, with some difficulties, to build an infrastructure for data. Infrastructure for data is something similar is in medicine, biochemistry. So we need a way to make our data fair. Fair means that has to be findable, reusable, reproducible. So every single experimental spectrum should be, in principle, in the future, reused by others, because this will increase the powerful of knowledge in a very strong way. It's boring, it's not so exciting as going with the mobile laboratory in museum, but I really think it's very important. And in this direction, we set up a digital working group in my institute. I have an institute of 190 persons. Half of them are archaeologists, the other half are from STEM, so science, engineering, mathematics, and so on and so far. So we are a wonderful example to try to build a data space where this data that we are producing, that are from what I show you, but also 3D model of buildings, geophysics of archaeological site, all sorts of things, can be registered, metadated, and made in an environment where to work together. And so this is the sketch of my person that are doing that. This is still a vision. We are exploring the possibility to use Arches, that is actually a platform of the Getty, and we are trying to see if it can be an option, working together with the institute that is doing informatics as a main business. We also have developed what we call Movida, that is mobile visualization data. The PhD student was from Barcelona, so for me Spanish, so I decided this name. She was very offended because Movida is Madrid, and Barcelona and Madrid were typically fighting. Nevertheless, this is Movida, and this is a software that was built around our way to proceed. So I don't know how you do the documentation on site, but the documentation is so important. So in this way, we were using the image, put there the point, each point there is a comment, each point there is the raw data. Something simple but very effective. And this is the idea of Movida. So can be some query and so on and so far. But we have to make this web available for everyone so that we can collaborate. You can imagine we could collaborate between you and Paolo from distance on the same set of data. This is the last slide. This is a project, a group of my institute that is very strong in virtual reality. It's something that now is very important. They are very well funded. And they decided to apply for this Codex 4D project. So I selected Codex, as you have seen, but just for a sort of order or beauty. We have other projects on other type of object, of course. But Codex 4D is trying to merge the virtual reality with the analysis and the use of this analysis. And these are the first example is going on from 6 months. And the idea is to merge 3D model of a book with the image acquired by thermography, okay? And so now very challenging is try to send the video. Good. Okay. No, da qui, così.
Yeah, solo per mostrarlo sullo schermo.
Sì, ma così va tutto intero.
Ok, ok. Tac. Ok, it's going.
So with the photogrammetry, they acquired the 3D model of the book. They typically do that for every type of object. And then they have what they call lens, that, for example, for archaeological application, they use the lens to make visible how the object or the monument or the site was in the past. So the lens is something that virtually show you some other information. So now we are trying to use this lens to show other image of the object that are coming from our technical image. Now you see thermography, because we started from that. It's not so powerful, but then since it's possible to have the lens for seeing the results of hyperspectral imaging, X-ray fluorescence mapping, we are trying to optimize this to have a way to work together and to combine the information from the object itself as a 3D object and the information that are coming from the technical image. Sì, ma si è visto, penso. Okay. And the very last slide. So. The very last slide is that one. And it's just to remember me to tell you that the very powerful of MOLAB is not to have the better laser, the better detector, but it's because it allows the co-working, really. It is for, is like this. So we are there with the object together with the other specialists, and we work together 2 weeks, and really the question came out together, and also the analytical strategy is decided together. And there is also, as was mentioned before, the possibility to have a first analysis of the results. So my colleagues, now I'm not so good anymore, can on the fly see some spectra. So on this first analysis, then will be done much more in deeper. They can, together with the conservator, archaeologists, so far, decided together the strategy. So go there, this is worth, this is not worth. And so I really think that this portable is making the work more effective in our field. So thank you.
Fantastic, thank you so much. Working together in an interdisciplinary way, using powerful technological tools. I think we are in the right direction. Questions? Yes.
With the Mesoamerican dyes and pigments, you mentioned that the clay has a more tunnel-based structure. Why is that important for the pigments?
The tunnel?
The clay.
This is very important because for this type of pigments, but there are colleagues that are more prepared than me on that. Anyhow, in this clay, there are this tunnel, is a sort of sponge, let's say, okay? Is a clay done like this. That means that if you have an organic molecule that is small enough and flat enough as a leaf, to understand ourselves, this molecule can enter, and if enter inside, is completely protected. So it gave the color to the clay, but is not under oxygen, under humidity, under light. So it's so protected that it can resist forever. Okay, so they were preparing this, mixing probably, for what we have understood, clay, the dye, water, and then some temperature. It's a temperature that allows some water to come out of the clay and the organic dye to enter. This is the concept. Then Giacomo Chiari has demonstrated that probably indigo is not really inside, but is on the grow. So at the end of this channel, if the channel is cutted, you have some valley, and so they simply are there with the hydrogen bonding that is linking the molecule to the structure. So to study the structure, we need X-ray diffraction, we need Raman spectroscopy or infrared that inform you on the hydrogen bond. It's not a chemical bonding, of course.
Yeah, so this is probably the first archaeological samples I took in the Roberto Gobetto's lab to, and probably brought me into the field, but very difficult also because sometimes there are like issues with all these techniques. We really have to be careful which technique or which approach is the best, because every topic holds challenges. We learned it from Steve, and I think it's very much about talking to each other in the interdisciplinary fashion to then tackle each problem with a specific set of tools. Steve.
I don't know if you can understand with the echo, but I found it difficult. But all the time I was thinking about this first sample from Herculaneum. You said it's carbon on carbon, but actually it's not quite. It's carbon that was prepared originally, the ink, and then the carbon that was carbonized during the heating of the ash. Now we've studied the diagenesis, or the chemical changes that take place in charcoal, in wood charcoal. And in order, well, it doesn't matter what, but there's a lot of chemistry going on quite fast. And this results in carboxylation, for example, of the ends of the graphite sheets. It also produces, in a way that I don't understand, strong fluorescence. And so I was wondering if one could hope or that maybe the diagenesis of those fragments is different between the ink and the base, and then home in, for example, and map at a high resolution carboxylate groups on the assumption that the substrate will be more carboxylated than the original suit.
Yeah, wonderful. The point is that we absolutely need imaging, because with point analysis it's impossible then to reconstruct. So now we are waiting for a new equipment that is able to do imaging in the mid-infrared for carboxylation. Yeah, exactly. So because we tried with point analysis infrared, but the differences are so small that you really need an image. If then you have an image and from this small signal you see a letter, so it is.
Yeah.
There are differences. It is difficult to say something. Because again, the line is very small. So really the statistic is done with the hundreds or thousands of pixels of infrared spectra. So we need this imaging. method.
Yeah, this is where big data could definitely make difference, because you have these tools, statistical tools, clustering. Yeah, no, but no. Here actually, it's just clustering of a big number of spectra. Correct.
And then one can tune
Absolutely.
the thing.
It's what we are trying to do. So to find some chemical that is differentiating the ink from the
yeah, but think in terms of diagenesis, not in terms of the original. The original is graphite on graphite.
Yeah.
In fact, just the diagenesis of charcoal pushes it towards looking almost like humic acids of soil. And so one could use that as a handle to think about it, even though we don't understand that very well.
Thank you.
No, but this is really a good point. I mean, there are two different approaches that we are talking about. One is understanding fundamentals of chemical transformations that will lead to a signal and differences in the spectra. Am I correct? And the other, which I think is really an uncharted territory, an interesting territory, where you use statistical tools to actually process big data, not one single spectrum, but hundreds of thousands of spectra that eventually give you a statistical confidence that actually there are differences. And now, once we have some sort of certainty that there are differences, eventually we need to close the loop and investigate the differences in terms of fundamental processes that occur. So it's really closing the loop, but using two completely different approaches. And this is where this data-driven title we particularly choose, because we do believe that there is a space now in which we collect enormous amount of spectra, enormous. And this sometimes really puts a limit to our human time to spend on each of these spectra, enough time to then extract something useful. This is where machines come really handy, because we can cluster with a single click and a highly and quite powerful machine, cluster 100,000 spectra. I'm doing it every day. And these subtle differences that perhaps have no meaning at all could appear. And then, of course, we need humans to actually make sure that these differences are understood properly and eventually interpreted. You need a signal. Yeah, without signal, trust me.
The computer will find the signal.
Yeah, that's true. Yeah, absolutely. And this then brings us to this second other side of the story, where machines can bring anything out, also not meaningful things, and we have to be very careful then in interpreting it. Any other question here? Yes, Juan.
So yeah, I was interested in the IR scanning of the artifacts. So I was kind of just curious, what would be like your opinion or perspective on the future of integrating modern technology with old, like, reliable methods. So in this case, you can see technology like these and like new phones and rising technology in modern day. So I was wondering how...
The English is too difficult for me, sorry.
Yeah.
No, maybe you can come here and speak. It's my fault, sorry.
Okay. All right. So how would you think that modern technology could influence like audience or other researchers' perspective of artifacts? Like, for example, do you think that these modern imaging processing systems are accurate enough that they could be used across museums instead of like physically bringing the artifacts to each examiner?
Okay, so you mean if with this virtual method we can avoid traveling and work together?
Yeah, like integration to like networking on online processing.
So, I think the future can be like this, because it's going to be very powerful because we put together a lot of thinking, a lot of researchers in the world. We are not yet in this situation, so we are not yet able to have a virtual environment for a proper study. There are virtual environments for visiting a museum, but still is not the same, and so very limitative, but probably there will be virtual environment for a sharing type of work. This was very strong, clear during the pandemic, of course, and especially for archaeologists. The archaeologists of my institute were not able to work anymore on site, so the idea of having something virtual to work from remote is nice, but we are not ready. If this was the question, I'm not sure.
Yeah, it is. I think you definitely hit the spot, and I think metaverse is still a big question.
So this group of people that are working with me, and they are all virtual, they call me in call. Instead of using Zoom, we have a virtual area where there is my avatar as director, and they are, and so.
Imagine what kind of avatar I could build for myself in this amazing world. Okay, thank you so much, Costanza. Actually, I will use a moment to advertise that we are co-chairing the Gordon Research Conference in 2 years on scientific methods in cultural heritage, and we are vice chairs this year. So have a look. Scientific methods in cultural heritage Gordon Research Conference that will be held in
16 July.
July 16 in
1 week.
Switzerland.
Second week of July.
All right, so thank you, Costanza, and we will close the session with Gilberto Artioli, professor, who I will use another, a little bit more time to advertise work that we have been doing. I met Gilberto some years ago in Jerusalem, and he wrote this amazing book on scientific methods in cultural heritage. Gilberto is professor, as I said, in the University of Padua, but he spent a significant amount of time at Getty Institute, I remember, and he wrote this book, and we had a wonderful conversation. We will be using his book as a textbook in our class this fall, some parts of the book. And in that conversation in Jerusalem, I said, I love your book, but there are some few things that I'm not using. And he's like, which things you don't use? And he invited me to send him like an email on like critical review of the book, just to really learn what parts are, at least in my opinion, more interesting than others. And then we came up together to actually write the second edition. This is the advertisement. Hopefully, inshallah, we'll have a new second edition co-edited with Gilberto, myself, and colleague of Gilberto, and she's in University of Padua. Yeah, exactly. And so, yeah, we will have this privilege to have a updated version of that fantastic book. So, without further wasting time, thank you, Gilberto, to be here, and we are looking forward to your talk.
Thank you. Now, since we're talking about data, let me just remind that databases are very important. I think this is not being enough stressed at the moment, and I hope that your virtual data, will be available, because everybody is building these limited data sets and databases. There are a lot of money for instrumental development and analysis of especially artworks, not enough for databases, and I think this is a crucial point to be made. Anyway, what I will show is something that we did a few years ago, because in Padova we have several centers working on the cultural heritage from different points of view, and we tested a method of working together directly from the field to the lab. And I think this is very appropriate for, that you selected this topic to this workshop, because I think we will be making a few points very important. Anyway, so all of you know Pompeii, or you will visit very soon, so I will not spend any time, but I will spend some time in showing the area that we investigated, is in the south part, in the Reggio Ottava. And actually, we focused on one specific building that was very unusual. It's outside the walls and is going from the floor. When you're walking in Pompeii, you are in the upper there, and up there. I don't know if you can see the pointer. And actually, it's one of the very few buildings that have 5 stories, okay? You have 5 stories, one upon the other. And this is the facade that was actually facing the river, the Sarno River, flowing in the south part of the city. And also the accessing of the building is very unusual. You cannot go from above or from below. There's this wall, and maybe the river was getting there. There was a small pier, a small stair, but nothing is left right now. But there are 2 tunnels going from the city, from the main road underneath the houses, and you can access the whole building from 2 tunnels. So very unusual, and all of the functions, architectural, facilities were basically unknown. Anyway, now we have a complete picture of the whole area, and I will go a little bit, in depth. And you can see the excavation of the early 1800. They were showing a part of the facade with a structure that is not existing anymore. And the story is that it was excavated in 1800, and then the whole building was reburied from when they were excavating the city, and throwing all the wastes in the river, in the slope, so it was buried again. Okay, and it was left there until the 1930s, where Maiuri excavated it again, and then it was used as a storeroom from the superintendency. But anyway, the real excavation were made by August Mau in 1890, and he writes a lot of, how he had to dig into the pile through this 5-story building, destroy some of the ceiling and to penetrate in the other rooms. And so we know that there are a lot of remaking, and, not the original structures. And again, this was one of the questions. I mean, what is original, what was remade in the 1800s, what was remade by Maiuri after the second excavation. This is Maiuri in front of the building, one of the rare photographs during the second excavation, and they're putting the facade on light. So we developed a project funded entirely by the University of Padova, and of course Massimo Zanna was very happy that we were going there with a bunch of people and the money also to do everything. We called it MAC project, and you see already, I will not go into the details, that we had 3 units. I was leading the archaeometric unit for the materials, but we had extensive archaeological team and also an engineering team. So already from the start, we were planning the project from the engineering, archaeometric, and archaeological point of view and interacting together, which is very unusual. And I think there is a strategy behind and a method to be learned somehow. This is part of my unit on the materials that we were visiting. Actually, it was a period where there was this beautiful Matuzai sculpture in Pompeii, which I think they were fitting very well. Anyway, I will not go into the aims of the project because I will focus on some of them. But at the end of the project was, we had several publications. And actually, they are using some of the data in planning the complete restoration of the area, not just of the building, but the whole facade that was collapsing, and also for interpreting the use of the building and valorizing it, because after you restore, you should open it to the public and understand why and how it was used. So there was a full issue of the Journal of Cultural Heritage published on the basic, some of the results, not all of the results of the thing. The very interesting thing is that engineers, scientists, archaeologists, they were together in the field. We spent about 1.5 years, 2 years in working together in the field, and as Steve was pointing out, I mean, in the field, looking at the structures, you discover things that are really, they are not just in the book report, especially of the 1800, and you understand how you should interact, how you should proceed with the analysis, and which kind of samples you have to take, and what you can do with the samples thereafter. Anyway, so these are some of the measurements we did in the whole area, and I will just briefly, show some of the results. The first point was to, of course, survey and measure the whole building in detail. This is the photograph of the orthophoto of the facade in great detail, and we actually needed that as a start because every single sample, every single piece was we were able. This is 100 meters facade. It's not something like a small excavation. And then there are 5 stories building, the whole thing's up to the rock and down to the villas and the top. So it's a huge area. But it was all mapped in great detail so that every little piece of mortar, every single brick, everything was actually, could actually pose, in the precise, GIS and, actually, the project also helped in redefining the coordinates in Pompeii that was a local setting into the global coordinates, and so that we could actually just replace, everything in the global world coordinates, geodetic. And so now we have the full mapping, internal and external. There was laser scanning, of course, other than photogrammetry. Everything is fitting together. And we were also able to reach places that were not yet excavated and, try to understand the evolution of the building in all sorts. And this was the basis because all the other operations were actually inserted into this frame. And of course, the first thing was to understand the architecture and try to put the chronology of the different, parts of the architecture into their development. And now we do have a full, chronological history of the architecture, the palimpsest of the architecture, and we know exactly when and which part, they was built and when and for which purpose, up to the destruction in, 79 AD. So there was the survey, the architectural interpretation, And then, of course, there was geophysics going beyond the facade and just the, laser photogrammetry and whatever. And we could actually see there was a whole area, for example, here. We didn't know, and they didn't know whether the arcades were big storerooms were continuing or there was actually a rock. And there was an area of the building that actually had a landslide, so there was also the geological interaction of the architecture and the building together. So again, the geophysical and the geological part were very important. We also looked at the stratigraphy out of the building and tried to see where was the best place in order to do a small archaeological excavation. So geophysics helped a lot in defining which place we could find the original stratigraphy of the river, the eruption, fallout, and the subsequent, rubbish, re-excavated. And actually, we could interpret this beforehand, before doing the excavation, and that everything was proved by a small trench perpendicular to the building that actually was confirming, all the observation that we did beforehand. So again, the interaction between the building, the archaeology, the geomorphology. Of course, we were all working together in the field, and we could see very well, the direction of the fallout, what kind of pyroclastic flow was actually, going on the top of the original layers, and of course the excavation, of course, confirmed and clarified some of the details. I'm not going through, but again, there are objects that were, in the rubbish before, coming from all over the Pompeii. There is the rubbish that was actually brought by the flow during the eruption, and then, of course, the original stuff on the layer. So at least 3 different events to be investigated in great details. Here you can see the original surface of the river before the eruption layers, and then the rubbish on the top that could be mapped in geophysical with geophysical means beforehand. And then there is, a sort of trying to understand the building from the architectural point of view, in the engineering point of view, because of the restoration. So every single masonry was actually tested in depth to see the degree of alteration and the damage that happened during the eruption, and every single structure was actually, tested mainly with pulse velocities in order to understand, the static, let's say, mechanics of the building in terms of planning the restoration and what needs to be done. But also there was ample modeling from, we put monitors, of course, for 1.5 years. We could see the dynamic of the structure, and there was a complete assessment of the hazards from future and past earthquakes, okay, on the building, and a complete modeling, for example, of the possibility of vibration of the building from the dynamic point of view, in order to build a risk assessment and, for the future, if the building will be open to the public. Keep in mind that, for example, in the second floor, in the whole part of the facade was at risk of detachment because there were 10 centimeters crack on the floor. So we really needed to develop, the full building plan in order to stabilize it from the engineering point of view. And then, of course, we went in. I'm just skipping all the details of, the modeling of the vibration and normal vibration modes of the building. And we started to look at the materials, which is more my part. And first of all, to get a clear idea of all the building materials they used, from the lithics, from the bricks, the man-made and the mortars and everything. And of course, by knowing, in details the mineralogy and the petrology of the materials and a clear idea of the geology around, we could actually locate the provenance of every single brick in the building. Okay, so we know exactly where it was coming from, where the quarry was, and when, in which period. You can see that, for example, the early basement and foundations were made of materials which are very different from the later stage. And again, we could put, into the chronology the use of materials from the local area. Okay. Which is also important in understanding the societal and economic needs of the period in different periods. And I'm not going into the details, but again, there are different construction, techniques. But very important, we could identify easily. Here, you can see it very well, what is the original and what is the, remake of the 1800 by Mao, but sometimes it's invisible from the aesthetic point of view, and of course the materials analysis tells you very, very well. As a matter of fact, we went into the details of the mineralogy of every single material, and what is a general analysis that you can do. We can carry out a detailed quantitative analysis of all mineral impurities in each mortar or in each brick, and through advanced PCA or other means analysis, we could, separate what you couldn't discriminate from a major element point of view by adding the trace elements. Every single mortar and the use of every single mortar could be very well distributed. For example, I will just mention this, the facade that was actually exposed towards the river and the sea breeze was much more pozzolanic and with a higher content of grog and crushed pozzolanic materials. The internal part of the building was built especially with a totally different kind of mortar. And you can identify the use of different binders, for different walls, expressly for the purpose. And then the last part, that again I'm skipping very well, it was of course the facade. The third floor was a bath. That's why they called the Terme del Sarno, because there was a public bath. And this is the frigidarium in very bad conditions after they being re-excavated. But that at least we had plenty of samples. I mean, in situ analysis was good, but we had plenty of samples to be taken. And actually, we have a fairly good database of pigments and mortars from the whole sequence of development of the building. And of course, we do have one thing we did, actually Yotam helped a lot in that, is that yes, we do have the the visible photograph placed in photogrammetry in all single environment, but for a few rooms like the frigidarium, that was especially nice. We were able, through the combination of X-ray fluorescence, diffraction, and multispectral imaging, to build a palette and identification directly of the pigments, so you can actually overlay the pigments on the whole visible image and tell directly where the ochre is, where the Egyptian blue is, where the other pigments are distributed in 3 dimensions, which is going in the direction, of course, that Costanza is doing. And in here, being a limited palette, of course, of the Romans, they were using no more than a dozen pigments in different mixtures, it was very easy, also from the visible images to identify the mixture of the different pigments. And of course, then we have the stratigraphy, and I have to say that despite the fact that you can analyze them very easily, we know all the pigment and the techniques, there are still things that I don't understand. For example, I don't understand why they were putting blue underneath the black coating. I don't understand why they were putting yellow underneath the red coating. Maybe it was changing the hues a little bit. It was changing the color slightly. Definitely, you can tell that they were made just one after the other. So it was not just the wife coming home and said, I don't like it yellow, paint it red. Okay? It was just on purpose made during the making of the stuff, and I still don't understand, what was the purpose of that. And then, of course, there is the whole, efflorescence and alteration, all the salts. Unfortunately, many of the salts were actually produced by the use of cement in the early 1900s, but some of them are coming from the rock, which is volcanic and contains chlorides and other things. But we can differentiate, that the restoration must act differently, when there is one type of alteration and the other one. And this is something that the restorers need to be aware, that they cannot treat all the different walls in the different areas in the same way. And I'm not going into the details. And of course, all the information that we provide is useful also to, reconstruct, the historical decoration of the building. And starting from the original, you can see that even when you have, I'm not going into the details, but even when you have a very nice and detailed reproduction of the original made before the alteration of the stuff, it is wrong. That the painter or the decorator, they added some part that are not there, they were never there. They missed some part that, that it was there, it was, just simplified by the drawing. So even when you have detailed historical records, because they can be wrong. And just, materials analysis help you a lot in this part. This is part of the, the digital enhancing and this rediscovering of the details of the pictures that are not visible anymore. You can see, some of these palms, for example, and the crocodile coming out. They are almost, disappeared completely, but you can bring them up, of course, if you know the digital enhancing of the old pigments that are still there and measurable. And this is the final reconstruction of the stuff. And I think, I just browsed very quickly, but you see the amount of work that we did in 1.5 years cannot be done by just, allocating slots of the work if you are not coordinated, okay? The amount of stuff we did by working together in parallel, in synchrony, in 1.5 years, it would take maybe 15 years, if you are planning the different operations separately in sequence. I thank you very much for your attention.
Fantastic. Yeah, this is definitely a great example of working all together and collecting a lot of data. So we have time for questions.
Can you ever tell when, like, a natural disaster happened, like an earthquake or something from the ruins? Can you tell when, like, a certain thing happened?
Well, there is ample evidence. As a matter of fact, some of the rooms were completely dismantled, and they were dismantling and in reshaping when the eruption took over. Okay, there are a couple of mosaics that were actually, brushed and piled already before the eruption because of the earthquakes happening 20 years before. So we can actually see what happened in the ancient times, the earthquakes. There are one of the things they didn't know, for example, is that in the back of the building, in the the stairs coming from the second to the third floor, there's still part of the original wall of Pompeii, you know, a century before Christ, that were never seen, you know, and they're barely visible in other places. So you can see everything, okay? The original wall, the reconstruction above, that they were destroyed in the 3rd century, they were rebuilt, there was another store happening, and then there was an earthquake 20 years before, and then they were replenishing when the eruption came, and then all the sequence. Yes, you can do that.
Yeah, that's a great question. Along these lines, so you have these evidences of, you know, historic drawings of how the things look like, maybe even at the beginning, at the very moment of excavation, and then how things evolve. What is your opinion on you know, this challenge that we do have of things fading away with quite quickly after they are excavated and after the
thermodynamics,
things.
Right?
Yeah, but you know that's exactly. I'm not sure that is exactly the same compared to standard weathering of our materials. Is there a difference?
Each material is behaving differently, okay? And the problem is that whenever you bury an object, okay, then it will reach quickly or slowly an equilibrium with the buried environment. And when you get it out, it's a thermodynamic jump. And it starts, you know, altering and changing again. You know, you are reacting kinetics in a different way, because then maybe you are more oxidizing, more light, whatever, okay? The only thing you can do is to slow it down.
Yeah. Just specifically, if you think about Pompeii, just excavated and how it looks now, what
to do?
Was it more colored?
Absolutely. You maybe you have seen the villa in Positano that was just excavated last year, two years ago.
Yeah,
I mean, the yellow and the blue are, you know, they look like made yesterday. I mean, it's a total different color with respect to the hue and the vivid, you know, enhancement that you see in the, what, you know.
Yeah.
Totally different.
Challenge of being in a museum at open air, and I think it's really
this is of course, you know, philosophical question.
Yeah,
I mean, what do? You do excavate knowing that you will reactivate the thing, or you let it there. Yeah. You know, this is especially true, for example, for petroglyphs. Okay, just talking to the completely different environment. Sure. We have millions of petroglyphs all around the world with different climates, you know, from the desert to the virgin forest, and they will be lost. There is no way out. What do you do?
Yeah.
And there is no real way to preserve it, because as soon as you change the porosity of the surface of the stone, whatever stone it is, from a granite to a sandstone, you are condemning them to loss.
And then the philosophical question is, should we let it go? Should we slow down? What exactly
in Scandinavia, as soon as they found a petroglyph, they rebury it. They map it and they rebury it. I mean, because that's the most stable environment. You know, they've survived for 1,000 years. Well, they are Vikings, so no more. But you know, at least they will survive another 100 years or so. Whereas if you take them out, you've seen the Val Camonica or the Mont Bégaud in France. You know, after, you know, and whatever they do, it's worse.
Great. I see some faces, friends here. Evelina Cristolina is the president of Egyptian Museum, and I'm so glad to.
Now, just a short hello to all you all. Sorry for not being with you this morning, but I had to stop by the traffic. You have seen probably they're shooting Fast and Furious here in Turin, and half of the city is blocked. But at least I see you now. I hope you are having a good time. You do? Yeah, great, exciting. Where are you coming from? Boston, of course, but where from? All over the world?
All over the States.
All over the States. That's good. Good. Are you going to stay this afternoon as well, I heard? Yeah. And I just came back from London. There's no one from Argentina? No. I just came back from London, where I was attending the match, football match, soccer match, as you say, Italy-Argentina, but there are no Argentinians within you. No one. So enjoy. No, they played terribly bad. That's why I was going to congratulate the Argentinians, if any. But I see them. You're going to perform this afternoon as well, Enrico? Yeah, heard so. Yeah. How you doing? Good? Nice to see you back. After the pandemic, we were all blocked, stuck everywhere. But so nice to see you here. I see Professor De Martino is coming over, his next conference. We never stop working in here. So enjoy, have a nice lunch, I believe, and you'll back here in 2:30, if not wrong. Thank you.
Yeah, thank you so much, Evelina, for... No worries. Thank you for giving us opportunity to come together and bring all these fantastic people to one space, physical space. That's true. We have a great... Thank you so much. Thank you.